Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 2, focusing on subtopic of 2.3 Hess's law. So we're going to focus on question 6b, 7 and question 8 and 9 respectively. So without any further ado, let us start. So for question 6b, the enthalpies of formation of ammonia, hydrogen chloride and ammonium chloride are negative 46.1 kilojoule per mole, negative 92.3 kilojoule per mole, and negative 14.4 kilojoule per mole respectively. So for the first question, we have to write the thermochemical equation for the formation of each of the above substances. So in order to do this question, we have to look back at the definition for the enthalpy of formation. So this is covered in the lecture 1.1 part 2, and if you haven't watched that, please watch it now before proceeding. Okay, and this excerpt are taken from the lecture video where the standard enthalpy of formation basically refers to the heat change when 1 mole of compound is formed from its element under standard condition. Alright, so the question asks here to find the formation of the above substances. So it doesn't mention about standard, so we can ignore the standard condition here. Okay, so basically the idea for the enthalpy of formation is you need your product to be in 1 mole because it says here 1 mole of a compound is formed. Okay, so let's say if you are producing for ammonia, NH3, so you know that you need to combine nitrogen gas with hydrogen gas and you need to produce ammonia. So here need to be 1 mole. Okay, so now we need to balance the equation. For example, for ammonia, because it got 1 here, right? But here is ammonia gas, which is gas here. So you have to write 1/2 in order to get 1 on each side. And for hydrogen, it needs 3, but here got 2. So you can write 3/2. Okay? And this will be aligned to the enthalpy of the formation definition for ammonia. And then it asks us to write the thermochemical equation. Means that at the right hand side of the equation, we need to write the enthalpy value, which is negative 46.1 kilojoule per mole. Alright, so if I were to put that nicely, I will write it this way, which is half N2 plus 3/2, because it will get 3 here, 3 hydrogen, and 3 hydrogen on that side in order to produce NH3 gas. So we will do the same for the hydrogen chloride and also ammonium chloride, where HCl is basically produced from hydrogen gas and chlorine gas. Okay, and it here need to be 1 mole. So we need to do 1/2 here and also 1/2 here so that we can get 1 hydrogen, 1 chlorine in order to produce 1 hydrogen, 1 chloride, which is hydrogen chloride in the product side. And we also need to write the enthalpy value here, which is negative 92.3 kilojoule per mole. Alright, so this one I write it nicely here. Right? And now the last part is we need to find the enthalpy of formation of the ammonium chloride. So ammonium chloride is NH4Cl, which is in the form of gas as well. And then we need to combine nitrogen gas plus hydrogen gas and chlorine gas. Okay. So here need to be 1 mole because the definition say 1 mole of a compound, which is ammonium compound, is formed. So nitrogen need to be 1, so we can do 1/2 here so that we can get 1. Chlorine also need 1, so 1/2 here. And hydrogen needs 4, but we got 2 here, so we can put 2 mole here. Okay, and don't forget the phase because the phase is compulsory. And the thermochemical equation needs to have the ΔH, which is negative 14.4 kilojoule per mole up here. Alright, so if I were to put it nicely, I will get the same as I've constructed here. 2H2 gas plus half Cl2 gas plus half N2 nitrogen gas produces 1 mole of ammonium chloride with the enthalpy value of negative 14.4 kilojoule per mole. All right, nice one. Now we're going to do the part 2, which is they calculate the enthalpy change for the reaction of ammonia gas reacting with hydrochloric acid produces NH4Cl. All right, and you can find this based on the algebraic method from the equation that you have constructed here. All right, so your target equation is you need to find the enthalpy change for this one. So NH3 plus HCl gas, NH4Cl, but you don't know the enthalpy. So you can do that by looking at the equation that you have constructed. Okay, so at this point, it is very, very important to know to construct the thermochemical equation, because once your equation is strong, you will find it very difficult to proceed with the other question. All right, so make sure you understand this part and always come back to lecture 1.1 part 2 in order to further understand on how to write the thermochemical equation. Okay, so as what you can see here from our first equation that's been constructed, the NH3 is on the product side, but here NH3 gonna be on the reactant side. So we can flip the product into the reactant and reactant into product, and our thermochemical equation from negative gonna be positive. So we can do that one first, okay, and ensure that you change the sign and change the reactant to product, product to reactant and reactant to product. And then from the second equation that you have constructed as well, you can see that HCl is on the product side, but here is on the reactant side. So you want to flip it again. So product to the reactant and reactant to the product, and hence your enthalpy gonna change sign as well. All right. And the next one, as what you can see here on the third equation, NH4Cl on the product side, NH4Cl on the product side. So I think you can use the equation straight away and use it directly here. Okay, because it's already on the product side. So NH3, NH3, same position. HCl and HCl, same position. NH4 and NH4Cl is in the same position. Okay, what's in the reactant will be in the reactant, and the reactant going to be in the reactant, product going to be in the product side. So the other stuff can be cancelled out. So product cancel with the reactant here. Half Cl2 in the product will be cancelled with half Cl2 in the reactant, and then product plus product. Okay, so you're gonna got 4 over 2H2, which equal to 2H2. So this both can be cancelled out with the reactant here. Okay, and so when you total up everything, you will get NH3 plus HCl equal to NH4Cl. Okay, so 1, 2, 3, 1, 2, 3, and it's the same as the target equation that we have constructed in the beginning. And our delta H here refers to the addition of the thermochemical equation that we have did. So delta H is equal to positive 46.1 kilojoule per mole plus 92.3 plus negative 14.4, because we doesn't change the position. So delta H that we will got is positive 124 kilojoule per mole. All right, so that's for question tutorial 6b. Now we're moving on for tutorial question 7. So nitrogen oxides undergo many interesting reactions. Calculate delta H for the overall equation of 2NO2 gas plus half oxygen gas into N2O5 solid. Okay, so our target equation is 2NO2 gas plus half oxygen gas going to N2O5 solid. So we can find the enthalpy from the equation that they have give in the question. So as what you can see here, N2O5 in the target equation is in the product, but here is in the reactant. So you can flip the equation so that you will get N2O5 in the solid state and here in the gas state. And when you flip the equation from the reactant to the product, the delta H gonna changes sign as well. So you get negative 2 to 3.7 kilojoule. All right. Okay. So here I change it to that side and I change the sign. All right. Now, as what you can see, N2O5 is the same. Okay. But now I need NO2 to be on the reactant side so that it is the same as this one. Okay. So I need to bring this to the reactant side. So it's going to be NO2 gas equal to NO gas plus half oxygen gas, and my thermochemical equation gonna be, because I already changed the position, right? So it's gonna be positive. Okay, positive 51.7. Okay, so product is the same as our target, NO2 is the same as our target, but it needs 2 mole of NO2, so we further multiply it by 2. So we're gonna get 2NO2 gas equal to 2NO plus 2 times 1 over 2 is equal to 1 oxygen gas, and the enthalpy also need to be multiplied by 2. Okay, so everything needs to be multiplied by 2. 2 here, multiplied by 2 here, and multiplied by 2 here. So as what you can see here, the NO and NO can be cancelled out, and 3 over 2 and 2 over 2, which if refers to 1, can be cancelled out in order to form 1 over 2. So here 2NO2 plus 1 over 2 equal to N2O5 gonna be the same as our target equation. Right? So we can add up the enthalpy together, and which is negative 2 to 3.7 kilojoule plus 103.4 kilojoule, and lastly we get negative 120.3 kilojoule. All right, so the enthalpy for the overall equation for our target equation is negative 120.3 kilojoule. All right, nice one. For question tutorial 8, given here is sulfur, which is in solid, reacting with oxygen gas in order to produce sulfur dioxide. So the enthalpy of the reaction is negative 297 kilojoule. And also given here is the thermochemical equation of sulfur dioxide reacting with oxygen gas in order to produce SO3 gas. And the enthalpy of the reaction is negative 99 kilojoule. So we have to calculate delta H for this reaction using the energy cycle method. So we need to find the delta H for the S sulfur solid with oxygen gas in order to produce SO3. And we have to do that in terms of the energy cycle method, where we could not do the energy and where we cannot do the algebraic method. Okay, so we have to do the energy cycle stuff. All right, so this is our target equation. So sulfur reacting with oxygen gas produces SO3, and we need to find the delta H here, so which we don't know. Now we have the info of S solid plus oxygen gas produces SO2, which is negative 297. So we can make another arrow here in order to produce SO2. And the enthalpy for the reaction is negative 297 kilojoule. Okay, so you're done with this equation. Now you look at this equation here. SO2 going to SO3, and the other reactant is half oxygen gas. So you can make another arrow from SO2 going to product SO3, and you add up another reactant on the side. So you can add another reactant here, and the enthalpy of the reaction from SO2 plus 1/2 of oxygen gas in order to SO3 is delta H is equal to negative 99 kilojoule. And as what you have learned in Hess law, the energy change for a reaction going from A to C or from A, B to C is the same. So the enthalpy change in a single step is the same as in the series of steps. So you can say that HF is equal to H1 plus H2. Okay, where here A going to C, and here going to A, going to B, going to C. So as long as the initial and the final point is the same, then you can see that the enthalpy change going to be the same. Here equal to up here. Okay, so we need to find delta HF, where delta H1 is equal to negative 297 plus delta H2 negative 99. So delta HF that we gotten is negative 396 kilojoule. Alright, okay, for question 9, acetylene C2H2 is a gas used in welding torches. It is produced by the action of water on calcium carbide CaC2. Calculate delta H for the acetylene in kilojoule per mole by using the thermochemical equation given below. So we were given a lot of equation here, and we need to find the enthalpy of the formation of acetylene in kilojoule per mole. So we have two ways. First, we can use the energy cycle method, as in the previous example, or we can use algebraic method. Okay. But I will suggest you to use algebraic method because it is much easier to do so when it involves a lot of equation. Alright, so algebraic method is more versatile in use that we can use in order to find the enthalpy of the formation, especially when a lot of equations given. So let us use the algebraic method in order to solve the problem. So our target equation gonna be the enthalpy of formation of C2H2. So you know that the enthalpy of the formation of acetylene need to be constructed first. The equation need to be constructed first, where C2H2 need to be 1 mole. Okay, and it comes from carbon, solid, and hydrogen gas. Okay, and the enthalpy of formation is something that we need to find out. Alright, so hydrogen H2 is H2 here. So carbon is C2. So we need to have 2C on the reactant side. And remember, enthalpy of formation need to produce 1 mole of C2H2. And this is where we're going to start our problem solving. Okay, so 2 carbon solid plus hydrogen gas produces C2H2 gas. And we need to find the enthalpy of formation, and we can do that by rearranging this equation by using the algebraic method. So I'm going to start with this one first. All right, so I will maintain this equation as it is because you know that my target equation, I need 2 carbon here on the reactant side, and from this equation I know that 3 carbon is already on the reactant side. Okay, so I will just maintain it the way that it is. Alright, so delta H naught is equal to positive 462.3. So I'll take it that straight away. But in our target equation, I need 2 carbon. Here I got 3 carbon. So I will take this equation and I inverse the equation. So the product gonna be the reactant and the reactant gonna be product. So once I do that, the sign gonna change to positive. Okay, from negative here into positive. Product going to be the reactant and reactant going to be the product. So why did I do this? This is because so that we can get to the right target equation. 3C will be cut with the 1C at the product side so that we can get 2C. So it is the same as our target equation. CO gas and CO gas can be cancelled out here. Now I need hydrogen gas. Okay, 1 mole of hydrogen gas. So hydrogen gas, if we were to find it, it will be here. Okay, so first, this one is in a product, but we need it to be in the reactant. So we're gonna inverse the equation first. Inverse the equation. Okay, so when we inverse the equation, the sign will be changing. Okay, and second, we only need 1 mole, but here is 2 mole, so we can divide by 2. Okay, so let's do that. 2H2 plus oxygen gonna be on the reactant side and produce 2H2O. But then I divide by 2 so that I can get one hydrogen gas is the same as the target equation. So I divide by 2 and I inverse that. So the enthalpy for equation number 5 is negative 2 at 6 kilojoule. Alright? And as what you can see here, half oxygen and half oxygen here can be cancelled out. Okay, now I've used up 1, 2, 3 equation here. So now I need to find C2H2 on the product side. So I'll be looking at this equation here. So this equation here can be maintained because the C2H2 is on the product side. It's the same as in the target equation here. So I'm just going to maintain that. So there's no changes in sign. It's still the same. So it's just going to maintain C2H2. Okay, so 2 carbon, 1 hydrogen mole, 1 mole of hydrogen and C2H2 here has been selected. So I think we are on the right track. Okay, and as what you can see here, C2 can be cancelled out, C2 can be cancelled out. Alright, now for the last equation, this one done. Now last equation, CaO plus H2O going to Ca hydroxide. So I think we need to inverse the equation so that we can cancel out the calcium hydroxide here. So this thing need to be on the reactant and this one gonna be at the product. So we're gonna change the sign. Okay, CaO hydroxide solid going to CaO solid plus H2O. So CaOH2 can be cancelled out and cancelled out here. CaO and CaO can be cancelled out. Water plus water on the product side become 2H2O. Okay, the one in the box, 2H2O can be cancelled out with the reactant. Okay, and what's left is 2 carbon plus hydrogen gas. 2 carbon plus hydrogen gas, 1 mole of hydrogen gas produces C2H2 gas. Alright, so I think we are on the right track. And delta HF can be calculated by adding up all the enthalpy changes that we have constructed from the thermochemical equation. So delta HF is equal to delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5, which is this value here. Okay, so once we do that, we're going to add up, which is 65.3 plus 462.3 plus minus 126 plus 220 plus minus 2 at 6 kilojoule. So lastly, the enthalpy of formation that we will get is equal to 335.6 kilojoule per mole. Alright, so I think that's all for today's video. So remember, ensure that you write your target equation here and use the algebraic method when it involves a lot of equation here. And be careful to change the sign when you invert the equation. Alright, I think that's all for today's video. See you again some other time. Bye!